All right, we're going to get started on section 10.7, which is about Taylor series, and we'll also talk about Maclaurin series, which really is just a more specific, a specifically located Taylor series, let's say. Okay, so let's talk about a function. Let's just start with sine of x. So what we've learned in Calc 1 is how to approximate a curve with a line, the tangent line. So for instance, let's say we want to estimate the value, or the function, the function sine of x close to some value x equals a. So a can move around. So let's say we want to look at the point a comma f of a. And we'll add a slider for a. Okay. So there's our slider here. We can move this around. We don't want this to be crazy. Let's just go from negative pi to pi. Somewhere in that range right there. Okay, so we're free to move this point along the curve anywhere from negative pi to pi. And I guess we can zoom in a little bit more there. Okay, so for instance, if we wanted to come up with the equation of the tangent line, we know that in general the equation of a tangent line, call this, I don't know, let's call this y1. Okay, because it's a line is a first degree polynomial, so we'll call it line 1. So y1. So this will be a function of x, and we know that it is the value of the function at our value plus the derivative at our value times x minus a. That's the good old equation of the tangent line that we know from Calc 1. So we can slide this point around and we are matching the value. Now let's take a step back before we even, let's just forget about this for a moment. Let's just go back and let's take a look at what would a 0th degree polynomial be. Well, if we want to match or approximate the value of sine at a single point, really all we have to do is make sure that the y values match. So a 0th degree approximation of a curve would just be an approximation given by a horizontal line, because this line matches the y value at that point. So sine of a and y0 of a, they agree. But you can see that the slope doesn't agree. So if we zoom in really close to this point, you can see that even if we move a very small distance to the left or to the right, it's a really bad approximation. And the reason for this is because the slopes don't agree. If the slopes were to agree, what we would do here is we would essentially take the previous approximation that we had, but then we would add on a way that matches the slope. So in order to do this, we would need to figure out the slope of the tangent line, and then we'd multiply it by this x minus a, and that would give us a really nice approximation. So essentially what you have here is the usual equation of the tangent line, but maybe written in a slightly weird way, because instead of just writing f of a, I have this y0 of x. But this is really just referencing f of a, so it is the same equation. But the reason why I'm writing it like this is because I want to connect it to this idea of a zeroth order approximation, where we are trying to, we have this curvy function sine of x, and the first thing we could do, the very most basic approximation we could do, is just have the y values match at a single point. So if our point is a, x equals a, then we make the y value match there. So we'll let f of a be our y0 of x. But then if we want a higher degree of accuracy, so another order of higher of precision, let's say a first order approximation of sine of x, we would not only want to match the y value, which is taken care of by the 0th order approximation, we'd also want to then tack on this information about the slope, which is what f prime of a times x minus a is accomplishing. And now you can see that zoomed in at this level, you can look at the scaling. Oh, you can't see the scaling on the screen here, but in the x direction, this distance here, these major grid lines, not these minor ones, but the major, it is about 5/1000. So we're zoomed in pretty far. But now if we zoom out, you can see, so now these major grid lines are now 1/100th. And you can still see that they overlap very well until you get about here. You start to see the spread. They start to spread apart from right here. So that's pretty far away. And if we zoom out even further, let's go back to kind of where we were. Right here. Oops. And you can see at some places, like right here, when a is 0, for instance, when a is 0, they match for a very long time. But then as we move a around, like for instance right here, you can see that you don't have to deviate as far away before the approximation and sine of x begin to really spread apart. That deviation, that error increases more rapidly here than it does, let's say, closer to 0. They tend to stay together a little bit longer before the line and the curve begin to separate. Well, we can do the same thing again. We can say, okay, well, that's great that the line, and so our approximation, our first order approximation, the tangent line, does match not only the y value of sine of x, but it also matches the slope of the curve at that point. Now, what can we do next? Well, what information does the second derivative tells us? Because the first derivative tells us information about the slope of the function. So if we want to know information about the slope of the sine of x at or near x equals a, we would examine the first derivative. Well, what if we take a look at the second derivative? What does that tell us? Well, it tells us about concavity. So we do have a second order approximation. And this would be taking our first order approximation and then adding on some new information. Now, it just so happens that this information would be the second derivative at a divided, divide that by, hit a wrong keystroke there, divided by 2 factorial. Now, we can take a look later about where this why there's a factorial here, but for now, just take my word for it. That has to be there. Okay. So now you can see that if we move, we can see all 3 of our approximations. So let's zoom in a little bit more. So let's make sine. Let's see, let's change that color. I want to make that something a little bit more bold. Let's make that red. I want that to stand out a little bit more. And we'll make this point. We'll also make this red just to match. Okay, there we go. So now we can see that the red curve is the actual sine. That's our function we're trying to approximate. The green function, the horizontal line, was our 0th order approximation. It only agrees with sine of x at the y value. No other information about it agrees with sine. It's just the y value. Then we increase that to get this purple curve, which is a line, and it matches the curvature, or excuse me, the slope of sine of x at that point. So you can see that compared to the green, the purple does do a really good job, and the black does a really good job. But you can see what's going to happen here is that the purple curve deviates from the red curve, the true curve, more quickly then the black curve, which is our second order approximation, a quadratic approximation. Our quadratic approximation lingers closer to the true curve for a longer period of time. In other words, we have to deviate farther from this point of tangency, this point where we're approximating. This point here, by the way, is called the center. It's called the center. So in fact, let's actually go ahead and alter this to make this a C everywhere. I think this might be better for us when we move into Taylor series, since the common term that you'll see is C being used, not A. So let's just edit that real quick to make this match. There we go. All right. So now we can even take this a step further, as you might have guessed. So we can do a y sub 3 equals, and we'll take our previous approximation, the second order approximation, and we'll tack on yet another curve, and this will incorporate information about incorporate information from the third derivative. And this is going to be 3 factorial. Again, we'll talk about that in a later video. And then x minus c cubed. And I don't want this to be red. Let's see what else we can get here for our choices. Ooh, oh boy, oh boy, oh boy. Yeah, let's go ahead. Let's go ahead and do that. Let's try orange. All right. So now if we zoom out quite a bit here, quite a bit, very far away, we can see what's happening here. So we've got, let's turn these approximations off, and let's just look at the original point. So there's our point on the graph. So if we want to approximate sine, we can do the 0th order, which, you know, it matches the y value, but nothing else. Then if we want to incorporate the instantaneous rate of change, the slope, we can get this better approximation, or a refined approximation, if you will. y2, we do even better. So let's zoom in on there just a little bit more. Let's delete that, the line, and notice here that the curvature really matches. The fact that it's concave downward. So the second derivative is negative at that point. We are incorporating that. So the third derivative here, it even refines it even more. And if you zoom out, you'll get this entire sort of picture of all of these things together. But really, we don't need to think about them as a sequence. I mean, it can be useful to do that, but really we just want to notice how this approximation here is getting pretty darn good. Pretty darn good. If we zoom out a distance, it looks like, let's make this c value 1, just for ease of referencing it. So at x equals 1, how far can we deviate from the to the left and to the right of 1 and still have it look like the red curve and the orange curve, the true curve, and our third order approximation match? Well, to the right, it looks like almost all the way to x equals 2, just shy of x equals 2, maybe 1.8, right about here. That's sort of where they deviate. Zooming in a little bit just so we can get a little bit better of a view. I mean, here you can see they do deviate. In fact, the closer that you zoom in, you will see the deviation occur even more. So over here, we're all the way down to 1.4 now. You can't see the tick marks on the screen, but this is a 1.4. But the more we zoom out, as we decrease our resolution really, what is resolution? Resolution is our ability to distinguish two different things. How are we able to tell that two things are actually different? You know, it's like when you're reading something and you see lines from far away or words or something. If you are nearsighted, such as myself, if I walk far enough away from a sign or something and I don't have my glasses on, I can't distinguish individual letters or words or lines or shapes. They all kind of blend together and it just looks the same. So our resolution is our ability to distinguish or to determine when two things are actually different. So in this case, at this zoom level, for me, it looks like all the way to 2, and then all the way down here to 0. So from this zoom level, it appears that I can deviate a distance of 1 away from x equals 1 and still have them match very well. Now, if we increase by a bit, we can see that they do deviate. Maybe I can only get to 1.5 and all the way to 0.5. But the idea here is that if you wanted an even higher degree of accuracy, so right here it looks like they agree from 0.5 all the way to 1.5. Now if I tack on another one, let's do y sub 4, a fourth order, which will incorporate information from our previous approximation plus information from the fourth derivative. And if I get rid of that orange one, now look how much of an approximate, look how close it is. 0.5 is right here. It still looks like they're the same curve all the way down into almost past 0. Similarly, over here, we have to move all the way to 2. So that agrees for a very, very, very long time. Now, of course, depending how far away you are interested in the curve, you can see that they do deviate quite a bit, and then really here the error, we can visualize the error as the vertical distance. So pick an x value and just look at the length of the line segment connecting the approximation to the actual curve itself. That would be a visualization of the error. Quantitatively, the error would be that difference, so the length of that line segment. And then we can, of course, continue this process as much as we would like. We can do a fifth order approximation, which incorporates our fourth order approximation plus the next higher order term, which would be the fifth derivative. It's a little difficult to write all those primes out, but that is what we're doing. And we get this green curve. And it's even better of an approximation, at least in this little window. So the idea here is that this x value, where we're basing all the information, we are extracting information about the various derivatives of f at this point x equals 1. This is why we call it the center, because all the information that we are using to construct this, and this green one here is a fifth order approximation, all the information we need comes from the original function, but only looking at the x value that corresponds to the center, which in this case, the center x equals c is the value 1. Now, if you can imagine doing this process indefinitely, so not just the fifth order, not just the sixth order, but doing this indefinitely, almost like an infinite order, you can imagine that what would happen here is that we would actually get the true function sine of x under some conditions. Now, it's not necessarily obvious whether this series would converge or not. Does it converge? Does it not converge? So far, we've been looking at power series, which is exactly what this is. These are examples of power series, except for how we're getting these coefficients, a sub n. We are extracting them or building them or defining them in terms of the function itself and its derivatives. Now, we could have something that is a different function. So for instance here, we'll see what happens when we change our function. So let's change our function to x to the 1/3 power. So the 1/3, or let's do 2/3 power. That's what I want, 2/3 power. The reason why I'm picking this one is I want this annoying little cusp to be present. That's what I want to sort of investigate with everyone. So if we look here at this cusp, you should remember from Calc 1 that whenever you have a corner or a cusp, it is a point where your function is continuous but not differentiable. So this means the function exists there. Like, we can plug in x equals 0 into this and we'll get out a correct answer, right? 0 is in the domain of this function. 0 raised to the 2/3 power is 0. But as we get closer to this value, our derivatives are going to get screwed up because there is no derivative there. So for instance, what we'll do here is, let's take a look at so there's our 0th order approximation, our 1st order approximation, or sorry, 1st order, our 2nd order, it's pretty good, 3rd order, really nice, 4th order, interesting, and our 5th order, which, did I not click enter on that? Why is that not working? I guess I've used too many primes. Desmos doesn't like that. We'll stop at 4th order. That's fine. We don't need any more than that. Now look what happens as we approach this value. They're working as, like, this is still valid and true, even as we approach. But there is something that's going to happen here when we get to 0. Doesn't exist. This is undefined. If we actually take a look at the first derivative of this, function, we can graph this. We'll just graph f prime. So f prime is this function in blue. So you can see that as you approach 0 from the right, the value goes to infinity. Goes to infinity. And that's because the slope here, if you try to approximate with a tangent line, you would have, oops, let's get rid of that. As you move in closer to this line, the slope does approach a vertical line, and a vertical line has an infinite slope. It's positive this way, because it's a positive slope, but if we started on the left-hand side of 0, our vertical line that we get would be approaching a negative slope, if you just think of it as a continuous process. So Taylor series don't exist at all locations for a function because maybe there is a certain order derivative where the derivative doesn't exist at that location. But if you have a function such as sine of x, the function we initially began to investigate, this function, however, it is infinitely differentiable. It has derivatives of all orders everywhere. So no matter where you look in the domain of sine, which is all real numbers, pick a point, any point, and you are guaranteed to be able to take the derivative as many times as you would like. Whether that's 40 times, 5 billion times, or even orders of magnitude beyond that. So if you have a function such as sine, a function that is infinitely differentiable, then you can define Taylor series and look at them there. They do converge, and just because they converge at a single point doesn't mean that their radius of convergence, however, is infinite. For instance, you can take a look at the, such as the graph that we had, x to the 2/3 power. The radius of convergence would be some portion here. It's not going to go all the way to, there's this point 0 here, which causes problems. So this would converge in some area here, but it could never include 0 in that radius of convergence. So here, if I'm at, right here, we're at negative 0.3, so that means the radius of convergence here would have to be 0.3. Because if we move 0.3 to the right, we're going to hit that issue. We're going to hit 0. That's going to cause problems. So the location of these issues, these singularities, these poles, these discontinuities or points of limited differentiability, not infinite differentiability, that is going to limit our radius of convergence.